Swayam Prabha. Digital India. Educated India.
Well, a very good morning to all of you. So, in the last class we were discussing about the estimation of flow patterns, why it is so very important for estimating flow patterns, what are the different flow patterns which are encountered during in a vertical pipe, in a horizontal pipe of normal cross section, that means greater than half inch or so, and then when the pipe is heated both in the vertical orientation, in the horizontal orientation, we found out the differences in flow patterns, and then we had just started discussing on the flow patterns which we encountered when instead of air we introduce a second liquid. It can be either kerosene, it can be toluene, it can be anything. Okay. So, that was the next thing that we were trying to discuss. Well, so for what we had talked of was that initially what we found was that just instead of air, if we introduce a second liquid, in this case we have done it with kerosene, that whatever I will be showing you, they have been done in the multiphase flow laboratory of the chemical engineering department of IIT Kharagpur, and these photographs etc., they have been taken in the experimental setups which are there in that particular laboratory. Now, what we see is there are certain differences which come in when instead of air we introduce a liquid. Now, what happens when we introduce a liquid? First thing is surface tension is larger here, viscosity varies over a large range. In fact, we will see that if we have a low viscous oil and a high viscous oil, the flow patterns are remarkably different. That also we have observed. Okay. So, this whatever I am showing you today or at the moment, it is for low viscous oils. So, therefore, what we find is just because the surface tension becomes surface tension becomes large and the viscosity varies over a wide range. So, therefore, the distributions are different as compared to the distributions which you observe for air water systems or for vapor liquid gas liquid systems. Now, what are the immediate differences which we can see? There is one more thing. In gas liquid cases, the gas phase was a compressible phase, but in this case, in that way none of the phases are so very compressible. So, therefore, we find there are certain differences which step in. The fourth difference is, as I had already mentioned in the last class, that either of the phases can wet the pipe wall. So, therefore, for air water or vapor liquid cases, what we had, when we had a very high gas and a very low liquid, we had something like the annular flow pattern, okay, where there was a thin liquid film and a continuous gas core. Beyond this, we did not have anything. If we keep on increasing the gas flow rate, keep on decreasing the liquid flow rate, under unheated conditions, we find that the liquid film, it becomes thinner and thinner, the interface becomes smoother, the gas core becomes thicker, but nevertheless, we find that there would be an existence of a annular flow pattern. And as we go for higher gas and lower liquid, when the slip is very high, we get a smoother interface, and therefore, we do not get anything beyond the annular flow pattern. On the other hand, we found out that for for liquid cases, either of the liquid can wet the pipe wall. Now, surface wetting properties, they are not very important as far as when we are dealing with quite large pipes where your surface energy is much less as compared to the inertial forces or the inertial energy, gravitational energy, etc., etc. So, therefore, we found out that in this case, depending on the relative proportion of the two liquids, either of the phases can wet the pipe wall and either of the phases can remain dispersed in the second phase. So, as we have shown in this particular diagram, where we have shown kerosene water flow for low viscous oil oil water flows, we find that at low kerosene, high water, we are distinctly having a continuous water phase with kerosene dispersed in it, similar to the bubbly flow distribution which we had observed for air water cases. On the contrary, when we go for a high kerosene and low water velocity, we find that the entire cross section, it becomes blue in color, and in that bluish cross section, meaning that kerosene is a continuous phase, in that bluish cross section we find out small droplets of water are dispersed here. So, therefore, this particular phenomena, the inverting from one continuous phase to the other, as I have already told you in the last class, this is phase inversion. This occurs for liquid liquid cases and never for gas liquid or for any other two phase flow situations. The other thing, just because of larger surface tension, what we find for gas liquid cases, what we had found out? We had found out that initially we have bubbly flow, but if we keep on increasing the gas velocity, then what happens? A time comes when the gases, they start coalescing and they start forming the Taylor bubbles and the slug flow pattern comes in. On the contrary, in this particular case, what happens is, if we take a horizontal situation, then what had happened there, initially the interface was smooth for low phase velocities, then gradually a waviness sets in, then gradually the amplitude of the waves, they start getting larger and larger, and then finally we were getting something of this sort. Okay. But in this case, interestingly, moment the interface starts getting wavier, what happens? Shearing occurs here, and due to the high surface tension, the waves do not grow so much to form the slug flow pattern which we had observed for the air water cases. On the contrary, what we observe here? We observe that these waves, they break down and then gradually several droplets start to accumulate at the interface between the kerosene layer and the water layer. Here we get a dense dispersion of droplets between these two layers, and this particular layer this contains kerosene drops in water, water drops in kerosene, and this gives rise to the 3-layer flow pattern which we have shown in the third photograph in this particular case. Now, this 3-layer pattern which has a distinct kerosene layer on the top, a distinct water layer on the bottom, and some sort of a dispersed situation between the upper kerosene and the lower water layer, which gives it a 3-layer appearance. This was not evident, or this does not occur for gas liquid cases. This is the other difference that we have. So, generally for gas liquid cases, under normal circumstances, we never for gas liquid cases, we have the bubbly, slug, churn and annular flow. In this case, we have the bubbly flow pattern, we have the inverted bubbly, if you say, or in other words, oil in water flow bubbly flow pattern, water in oil bubbly flow pattern, and then we have the 3-layer flow pattern. These things are the differences which we did not have there. Just by changing one phase, by replacing the air phase with another liquid phase, low viscous liquid phase, that too we find that these are the ranges of differences. But interestingly, we find as the pipe diameter reduces, you can see from this particular slide, for a horizontal pipe, as the diameter is reduced from 25 millimeters to 12 millimeters, a tendency of slugging occurs. Definitely the kerosene slugs, they are not as well defined as the Taylor bubbles, but some sort of a tendency of slugging, it starts to occur. This will be much more clear if we see another, these things already I have told you, the 3-layer flow pattern and things like that. So, this is going to be much more clear if you see certain flow patterns for tolling water flow. Here you can very distinctly see slug flows, Taylor bubbles, just like the Taylor bubbles which we had observed for air water cases. So, therefore, we find that with miniaturization, the differences between air water flow and liquid liquid flow gradually reduces. as we approach miniaturization, since surface energy becomes more and more important, we find that initially just like air water flow, initially we had bubbly flow here, then gradually the bubbles start getting larger and we get distinct slug flow sort of a situation, and from slug flow, as we keep on increasing the toluene flow rate, gradually we do not come across a churn flow pattern. In this case, these toluene Taylor bubbles, they start coalescing and they form a distinct annular flow pattern, where there is a toluene core and there is a water film between the toluene core and the pipe wall. If we keep on increasing the toluene velocity further, then in that case what happens, in the entire tube toluene becomes the continuous phase and some amount of water droplets start to accumulate here. So, therefore, we find that under normal circumstances in liquid flows, we do not have this slugging tendency, but as we go to smaller pipe diameters, then the differences between air, water and liquid flows, they gradually reduce and we come across more similar flow patterns in the two cases. Okay. So, this shows the effect of fluid physical properties or the fluid type on the flow distributions. Now, instead of a low viscous oil, if we go for a high viscous oil, say lubricating oils, okay, or crude oil. Now, here I would like to tell you one particular situation. Initially, people used to study low viscous organic liquids and water flows, because that was what we were encountering in our practical applications. In petroleum industries also, the lighter oil fractions were being explored and therefore, low viscous oil water flows were studied in great details. Now, gradually what is happening is the lighter oil reserves, they are getting depleted, isn't it? All the lighter oil reserves, they are getting depleted, we are going deeper and deeper, and therefore, we have to explore and we have to recover the high viscous oils. And the other thing what has happened is, now the onshore oil fields are also getting depleted. So, therefore, we have to go for offshore cases. Moment we go for offshore cases, what is the problem? Transportation becomes a problem, because from beneath the seas it has to be explored and then from there it has to be brought to the oil exploration units which are on the shore of the seas. So, therefore, initially transportation was not such a very big challenge, number one, and number two, we were satisfied by dealing with lighter oils. But now what happens? Now, due to these two factors, the transportation of viscous oil has become a very big challenge. What happens whenever we want to transport high viscous oils, we need a large amount of pumping power, and there have been several attempts to reduce the pumping power. What people try to do? They try to mix up some amount of lighter oil with the heavier oil, so that its viscosity goes down. Another thing they try to do, they try to heat the oil at regular intervals, so that the viscosity goes down, but these things are not very feasible situations. Now, from two-phase flow, what we found out was that a very attractive solution can be proposed, and in fact, we are thinking of working with, in fact, the discussions have also proceeded, and presently a work will be done with ONGC regarding the reduction of pumping power for transportation of high viscous oils. What we have planned to do? We have planned to find out, or rather we have observed that there is something like the annular flow pattern, isn't it? For oil water cases, we call it the core annular flow pattern. What happens under these circumstances? Just like the annular flow pattern, there is a oil core here and there is a water film here. This is known as the core annular flow pattern. For liquid cases, it is nothing but the annular flow pattern that you have observed for the gas liquid cases. Now, in this particular case, we find that if we inject a very small amount of water in such a way that it is the water only which wets the pipe wall and it separates or it prevents the oil core from coming in contact with the pipe wall, then what happens? The frictional pressure gradient, it arises due to the contact of water with the wall. Is it clear to you? Why is the pumping power so high? It is so high just because oil is viscous and therefore, there is a very large amount of wall shear when oil has to be pumped. Now, suppose the oil is prevented from coming in contact with the wall. So, what happens? The frictional pressure gradient, it arises primarily because of the wall shear between the water and the wall. So, therefore, by this, if we can maintain this particular flow pattern, we have actually shown in our laboratory experiments that the pressure drop decreases so much that it is almost similar to the pressure drop which we will encounter if we pump only water through this particular cross section. So, can you imagine the reduction in pressure drop? So, the pressure drop almost for this particular flow situation, the pressure drop is almost similar to that particular pressure drop which we would encounter when only water flows through this particular pipe at the same mixture velocity. So, this results in a drastic reduction of pressure drop, and this leads to a drastic reduction of the pumping power required, and therefore, this is it is a very attractive proposition as far as oil exploration is concerned. So, therefore, this particular idea we had got from our studies of two-phase flow only. And interestingly, you would also be interested to know that we find that the tendency of formation of the core annular flow pattern, it increases with viscosity of the oil. That means, the more viscous the oil is, the more it has a tendency to stay in the core annular flow pattern, which is an extremely fortunate situation. So, therefore, as we go for a more and more viscous cases, we find inverted dispersed people have generally not found out for this high viscous cases, and core annular flow pattern occurs over a large range of flow velocities, and apart from core annular flow pattern, we have some sort of slugs, elongated bubbles, but mostly the flow pattern is core for all pipe orientations. So, therefore, we find that even when we are working with liquid cases, depending upon the liquid properties also, the flow patterns vary. So, this is very important. In this particular slide, I have shown the comparison between lubricating oil water flows and kerosene oil water flows. You can very well understand that maybe at high oil and comparatively lower water velocity, there is a tendency of core annular flow for both the cases. But please note the difference in waviness for the two cases. In this particular case, we are having an asymmetric wave, whereas in this particular case, if you observe, the waviness is definitely axisymmetric. Just because of the difference in the nature of the interfacial waves, the flow patterns which occur with decrease of oil or increase of water velocities, they are drastically different for the lube oil water case and the kerosene water case. You can see for the kerosene water case, we have kerosene dispersed in water, but here we have some sort of a slug flow, where these particular lube oil slugs, they are extremely sinuous, tortuous sort of a thing, and irregular sinus sort of a slug flow we have. So, therefore, you can see the differences in the distribution between lube oil water and kerosene water flows under comparable or under identical flow velocity conditions, same pipe diameter, they are for downflow situations. You can notice the differences in flow patterns just by a change in the viscosity of the oil that we have used. Okay. After that, I would like to show you, see, whenever you are working or whenever something is, any particular thing is being transported, pipe fittings are inevitable. You got to have T junctions, you got to have bends, elbows, contraction, expansion, these things have to happen. Now, when these things encounter, for single phase flow, what we do? We define an equivalent length and then we calculate the pressure drop accordingly, is not it? Now, in this particular case, we find even the distribution changes when we encounter such a situation. Why? Because whenever there is some particular pipe fitting, it imparts some additional force, maybe a centrifugal force, a centripetal force, something. Whenever some force is exerted, that depends how much of the force will be manifested, that depends upon the physical property of the particular fluid. So, therefore, whenever there is say two particular fluids of different density, then one tries to accelerate over the other. This accelerating tendency, if it is enhanced by the presence of pipe fittings, then naturally the distribution it tends to change, isn't it? For example, here I have shown you that kerosene water flow, again when it is flowing through a bend, what happens? In the upstream section there was water here, kerosene there. By the time it covers the bend, kerosene goes up, water goes down. So, naturally there is some sort of a film inversion occurring. If you, I do not know how much clear it is, there is some sort of a film inversion occurring. From the lower portion, water shifts to this particular portion, and this is one particular thing which a bend brings about. Then suppose we have contraction expansion, this is very evident. See, suppose we encounter an expansion, sudden expansion, what we find? Initially the flow was distinctly stratified wavy, okay, small amount of waviness was there, not much waviness. There was kerosene on the top, water on the bottom. Now, just after the expansion, what we find? It becomes a 3-layer or a dispersed sort of a thing. Distinct droplets arise, and these droplets are more or less suspended between a upper thin kerosene layer and a thick continuous water layer. In this case also we find another interesting thing. Initially in that upstream section there was a 3-layer flow pattern. Now, as I have told you, the tendency of formation of 3-layer flow pattern, it decreases with pipe diameter. For larger diameter only it is important, as we reduce the diameter, the tendency of formation of the 3-layer pattern, it decreases. So, what we find? Moment we encounter the contraction, from the distinctly 3-layer or maybe the dispersed sort of a pattern, we get distinct oil plugs under these conditions. So, this also gives you an idea of how the different types of pipe fittings, they tend to affect the flow patterns. Okay. This is another particular case which I would like to show, a very interesting case when we were trying to study kerosene water flows through the orifice meter. Now, in this particular case, if you observe, say here, okay, what we found? We had started with a smooth stratified flow. The orifice is located at this particular position. So, we had started with a smooth stratified flow. Just after the orifice, what happened? It became a completely dispersed flow situation, and more or less it ended up being a 3-layer flow pattern. So, from distinctly stratified we obtained a 3-layer flow pattern. Then again in this particular case, it was sort of a plug sort of a situation or a dispersed sort of a situation, but where the plugs were concentrated only on the upper portion of the pipe. From there instantly what we got? We got a homogeneous dispersion of the two phases, kerosene dispersed in the oil phase. So, therefore, we found what the orifice did for low viscous oil water flows, they served to homogenize the mixture. They reduced the separation between the two mixtures, and every time we find what is happening, if we start with stratified smooth, we get a dispersed. If we start with a plug, we get a more or less uniform emulsion. We start with dispersed flow, we get almost uniform emulsion. When we have a uniform emulsion, it becomes whitish in color. You must have observed emulsions, they are so well mixed, the droplets are so fine and they are so well mixed with one another that we cannot identify the difference between the two phases, and it becomes a uniform, a whitish, a frothy appearance. So, here it is very clear that the two phases can be distinguished clearly, but in this case it becomes a whitish appearance where nothing can be distinguished. So, from these cases what I want to emphasize is that we know pipe fittings affected fluid flow behavior, that you have seen in single phase flow as well, but in this particular case the influence is much more pronounced. Because why? Because whatever pipe fittings are there, they tend to influence the, or rather they either try to homogenize the two flows, the two phases, or they tend to separate the two phases. Usually when we have a bend, the bend has a tendency to it enhances the separation of the two phases. If we have bubbly flow downstream, upstream of the bend, we get slug flow in the downstream portion. Suppose we are having annular flow at the upstream of the bend, annular flow with droplets. What this bend does, it tends to separate the droplets from the gas core. So, it brings about a separation of the phases. So, therefore, what we find is that from all these things we find that even by using these different type of pipe fittings, we can get some sort of a change in flow distribution, which might be desirable for us, which might be undesirable for us as well. Okay? If we study these things well, if we know these things well, then probably we can use it to our advantage, or else two-phase flow will be exploiting us and we will be in a total mess in trying to control it. A very practical problem I will be telling you, which had actually come to us from IOCL. See, the thing is, I have talked about bends, contraction, expansion. What is another inevitable pipe fitting which we encounter in industries? T-junction. T-junction is something very common. Now, whenever something flows through a T-junction, say a horizontal junction also, what happens? Suppose say a gas liquid case is flowing. Okay. Now, whenever it encounters a T-junction, sorry, I will draw it in this particular way, it is a horizontal T-junction. What happens? The gas will have a tendency to move in faster because of its lower inertia, and the liquid will have a tendency to flow straight because of its higher inertia. Yes or no? So, therefore, we find a T-junction, it can be used as a partial separator also. So, very frequently, suppose we want to separate the two phases. So, therefore, in order to reduce the load on the main separator, what we can do? We can just simply introduce a T-junction upstream of the main separator. Some amount of separation will occur there. So, therefore, the main separator, it can be of a reduced load, it can probably operate at a higher rating capacity. This is one advantage. The other thing is, if you do not know that the T-junction can separate the phases, then probably what happens? Suppose you have a T-junction, say just downstream of a distillation column. So, you have designed the distillation column according to a particular feed composition, is not it? Accordingly, you have decided the number of plates, you have designed the distillation column, agreed. Now, there is just a T-junction before it. In the T-junction, what happens? Partial separation occurs. So, the feed composition with which you have designed, that feed composition does not enter the distillation column now. And what you find? You find that your distillation column is not performing well, and you do not understand why it has happened at all, is not it? So, therefore, you have to know these things. The practical problem which had come from IOCL was, they were operating under a particular circumstances, where in their distillation column they were introducing a feed of say crude oil and natural gas. This was being introduced in one of the distillation columns. Okay. Now, due to some particular reason, they had an enhanced supply of the raw material. Okay. Now, for this enhanced particular supply, what they have to do? Either they have to increase the size of the distillation column, is not it? Or in other words, what they can do is, suppose initially the entire feed rate was 1 meter cube, now it has become say 1.5 meter cube. So, now for what they thought of doing is, initially 1 meter cube was coming. So, now what they thought is that let the entire 2.5 meter cube come, we will design it in such a way that only 1.5 meter cube enters this particular distillation column, and 1 meter cube will be diverted here, and it is going to enter another distillation column, say DC2. Okay. And therefore, or else what is the other thing that you can do? You can simply dismantle this distillation column, and you can construct another huge distillation column capable of handling this 2.5 meter cube of feed which you have now. So, naturally, dismantling the whole thing, constructing a new thing, it is much more expensive. So, what they thought, no, this is not a very good proposition, we will simply bring the whole thing, we will divert it at a T junction, and then we will take them to two different distillation columns. In that case, what is going to happen? No, DC1 is already existing. So, distillation column 2, DC2 will only have to be constructed, and these pipe fittings, they are quite cheap. So, therefore, with another DC2 we can just perform the distillation operation, it is not going to be of much problem. But when they started doing this, what they found out was, the main problem was they found out that none of the columns were operating to their desired performance, and they were getting very surprised, because they thought maybe the design of DC2 is not correct, but DC1 was existing. Then also why was DC1 not giving the desired performance? They were completely at a loss to understand this particular situation. So, they came here and they contacted one of our faculties to know what can be the probable reason of this. What can be the probable reason that by just diverting the feed or just by dividing the feed, we are putting the same quantity of the feed, everything else is same, we have not changed anything, but DC1 is not operating properly. So, then we found out what was happening was that when they are using a T junction, this acts as a partial separator. So, therefore, more amount of liquid and less amount of gas is now being introduced to DC1. It was designed for a higher amount of a gas and a lower amount of liquid. So, therefore, now it is operating for a changed feed condition, and due to that particular reason, the performance was not getting proper. So, therefore, what was the suggestion that we gave? The suggestion that we gave was that you cannot take the entire feed mixture and separate it in that particular way. What has to be done? Say suppose the feed is in this particular, in one particular container, we have say gas, sorry, it is gas and liquid, let us say. What we have to do? We have to first bring the total, say the 2.5 meter cube, we have to first bring it to a separating, any particular sort of a separator, and separate the gas and liquid. Then liquid we have to take out from there, and this liquid have to be introduced or have to be diverted using a T junction according to the proportion that we require. Say suppose initially we required 0.75 meter cube of liquid and 0.25 meter cube of liquid. So, that we can do for the liquid separately. Similarly, for the gas again, let the gas be taken out separately and then let they be diverted across a T junction. Then this particular gas and this particular liquid, they have to be mixed up somewhere, from where they should be fed to the DC1, so that the composition is maintained here. Is it clear, or should I repeat this thing? It is clear? Repeat. What was the problem? Initially they were having a crude oil, natural gas, raw material mixture, okay? And in that particular mixture they were feeding it into a distillation column, and the distillation column was performing distillation, okay? This two phase mixture was a feed. Now, suddenly due to some reason they had an enhanced supply. Now, when they had an enhanced supply, what to do? The column was not meant for such a high amount of the supply, is not it? So, therefore, either a larger column had to be built to tackle this increased quantity of feed, or what they thought that no, it is too expensive and time taking also if you have to build a new column. So, what they thought, it is easier that well, let the column exist, we will introduce that amount of feed for which it is made. Say if it is made for 1.5 meter cube of feed, now we are having 2.5 meter cube of feed. So, we will introduce 1.5 meter cube of the feed into the distillation column, and the remaining portion of the feed, what we will do? We will just introduce it into a second smaller column. Okay? So, therefore, the things will be cheaper and we can perform distillation well. Now, what they did not, so what they did, the entire feed was coming, there was a T junction, they took out the required amount of feed which has to be fed in DC1, the remaining feed went to DC2. Agreed? What they did not understand, or what they failed to understand was, moment they are using a T junction, it acts as a partial separator. When it acts as a partial separator, it changes the composition of the feed for which the distillation column was designed. Got my point? So, therefore, when it changes the composition, therefore, the distillation column started underperforming badly. They were not able to understand the reason because they did not know that T junctions act as partial separators. Okay? So, therefore, they came to our institute for some suggestion. So, what we found out was that if the two phase mixture is subjected to a T junction, then definitely the composition will change and definitely the distillation column will not perform properly. So, what has to be done? Does that mean then a separate column has to be made? That is not at all a feasible solution. So, what we suggested is that whatever feed we have, bring it and separate it into the gas phase and the liquid phase. Okay? Divert the liquid phase separately using a T junction as I have shown here. Divert the gas phase separately through a T junction as I have shown here. Now, gas phase, when only one phase is flowing, then the proportions can be varied at will. There is no problem of composition changing, isn't it? Pure gas phase. Similarly, the liquid phase also the proportions can be varied, okay, by adjusting the diameters and things like that. So, therefore, by this process we could get the amount of gas and the amount of liquid for which DC1 was designed, right. So, now these two were mixed and then they were introduced in DC1, and the remaining proportion of gas and liquid, they were again mixed here and in one particular container, and then they were introduced in DC2. So, now both the columns were getting the feed composition for which they are designed and they started performing well. So, unless we have an idea of two phase flow, it is not possible for anybody to deal with these situations in a practical manner. So, this was one of the situations, and this is one particular practical problem I thought I will share with you just to show you how pipe fittings can be advantageous to us as well as it can be extremely problematic if we do not know how the pipe fittings are affecting the two phase flow situations. Okay. So, certain other things, well, the next thing which I would just like, I thought I will show you just to show you that how the flow patterns they evolve and how important it is for us to know the different flow patterns. We first found out air water or vapor liquid, it is more or less the same. Then instead of water we tried to introduce oil, we found out how it changes. We changed the property of the oil, we found out how the flow pattern changes. The tendency of core annular becomes more, and that is an extremely fortunate situation. Now, in this oil water flow, if we introduce a third phase, say water, then in that case what do we get? Sorry, we introduce a third phase, say air. So, now it becomes air kerosene water flow or air oil water flow, liquid gas flows. For that particular situation, what can we get? How does the circumstances change under this condition? We find that at very low flow rates, horizontal pipe, tendency of stratification will be there. So, immediately what we get? We will, at first glance what appears to us is, initially we had a gas phase and a liquid phase, or if it is liquid we have L1, L2. This particular case at very low flow rates we will be having G L1, L2, okay, which has been shown in this particular case. But we find that whenever we increase the gas flow rate by a very small amount also, there is a tendency of slugging and slug flows occur. Okay. The slug flow will be evident, the photographs are not very good I believe. From here you can see these are the Taylor bubbles which are there, and this is the liquid slug. Okay. Here the liquid slug portion is shown much more evidently. Now, we find that usually there is a tendency of slugging, and what we have usually for slightly higher air velocities, for moderate air velocities also, air tries to exist as Taylor bubbles, and in the liquid slug the distribution can be a number of types. One is water continuous oil dispersed, other is all continuous water dispersed, other is an emulsified flow pattern. Both for vertical as well as horizontal, we find these particular situations. Usually the range of slug flow increases here, and the distribution in the liquid slug, it can be oil dispersed in water, water dispersed in oil, or a stratified emulsified situation. For horizontal tubes, what we have? Horizontal tubes for very low velocities, we have the 3-layer flow pattern. Okay. As we increase the velocity, we find that slug flow sets in. We have something like huge slugs, just like we have in gas liquid flows, and we have a liquid slug and a Taylor bubble. Now, this liquid slug, it can either be stratified. So, stratified liquid layer can be there, stratified liquid slug. It can have droplet sort of a thing. So, therefore, we can have water in oil dispersed liquid slug, we can have oil in water dispersed liquid slug, and we can have an emulsified liquid slug as well. And interestingly, in this case also we find that in the liquid film between the Taylor bubble and the pipe wall also, there can be some particular, say it is a water film with oil droplets and so on. So, therefore, with the introduction of a third phase also, we find that more or less the patterns are the same type. It is usually slug flow, it can be a 3-layer flow, it can be a dispersed flow. Say when water is very high, kerosene and air both are at very low velocities, then we can have a completely dispersed flow also. Or say kerosene is very high, water and air are at very low proportions. Under that conditions, we can have a dispersed flow pattern also. Okay. But under for a wide range, we have slug flow, but even for these known flow patterns also, the distributions become slightly different by the introduction of the third phase. Why? Because if you have to analyze such flow patterns, you have to consider the Taylor bubble is fine, but for the liquid slug, if it is stratified, then some stratified model has to, some separated flow model has to be used. If it is dispersed, then some sort of a homogeneous model has to be used. These models we will be discussing later, right. Now, suppose these are some general flow patterns which we would like to discuss. You should be knowing the different types of flow patterns which exist under different conditions. So, this is about gas solid flow patterns. Now, where do we get gas solid flow patterns? Pneumatic conveying and fluidization. These are the two applications where we come to encounter your gas solid sort of flows. Okay. Now, in under such conditions, we get that usually the flows can be broadly classified into a dense phase and a dilute phase. You can very well understand the difference between the two, is not it? Dilute phase, very less amount of solid, larger amount of gas; dense phase, larger amount of solid. Now, the transition between the dense phase and the dilute phase, it is usually defined by the choking velocity. Now, we have two types of choking velocities. One is the different types of choking velocities that we have is, one is the slugging type of choking velocity, it is known as the accumulated choking, and the other one it is known as the classical choking velocities. Okay. Now, within the dense flow regimes, we have, for the dense flow regimes, if you notice, we have the slugging, the bubbly flow, the slug flow, the turbulent fluidization, the particle rain, and the separated plug, or this is almost like the plug flow pattern or the slug flow pattern in this particular case. So, we have these types of flow for the dense phase situation. Now, from the dense phase, if we have to shift to the dilute phase, the transition is usually governed by the choking velocity. Now, this transition occurs when the gas velocity is reduced at a fixed solid phase. Then under that condition, we find that we shift from the dilute phase to the dense phase, is not it? That the solid loading is kept constant, gradually the gas velocity is reduced. So, then we come from the we have a transition from the dilute phase to the dense phase. Now, there can be two types of we define two types of choking velocities. One is the accumulated choking, the other is the classical choking velocity. Now, accumulated choking velocity we get when the condition, when the dilute flow becomes non-slugging. For example, from here to here, when the condition when the dilute flow becomes non-slugging is called accumulated choking, and this is related to the accumulation of solid at the bottom of the pipeline. Okay. So, therefore, when it is the transition becomes, or rather the dilute flow becomes non-slugging, we have the accumulated choking condition, and the condition when the dilute flow becomes slugging flow, from here we get a slugging flow, then it is called the classical choking. It is related to the formation of this gas slugs. Now, remember one thing, both pneumatic conveying and fluidized bed systems, they are designated for different tasks, but more or less they have got many similarities. For example, for both these systems we find in the dilute flow we have different phases like turbulent fluidization, fast fluidization, slugging fluidization, bubbling flow, fluidized flow, and all these types of things both the systems they have. And the dilute flow regimes, they are characterized by suspension flow at high gas velocities and low solid loading. Okay. We have this suspension velocity or this suspension flow we have. Now, remember one thing, although the fluidized beds as well as pneumatic conveying, they have the same type of, or rather they are used for different purposes, more or less the same type of flow patterns they occur. But the thing is, for fluidized bed we find that for pneumatic systems this particular suspension flow, it is a desirable condition. We want to have suspension flow for pneumatic conveying, and for fluidized bed this particular regime, it occurs just as a bypass process when we want to empty the column or when the inserted sample has a wide size distribution. Only under that condition it occurs. So, under certain, depending on the application, under certain situations we might want a flow regime or we might want to avoid a flow regime, but whatever exists they are more or less similar, no matter what is the application for which we use it. The other thing is, when a wide particle size distribution is there, we find that the large particles they are fluidized at the lower part of the column, and the fine powders they are carried over by the dilute flow regime. These are quite evident things, and when we reduce the gas velocity, what happens? The suspension flow it gets halted, and when the suspension flow gets halted, we find that some particle clusters they begin to they might appear, and the flow regime which occurs after the appearance of particle clusters, this is known as the fluidized flow. So, initially what happens when we reduce the gas velocity, the suspension flow it gets halted, particle clusters start appearing, and just after this we get the fluidized flow regime, or the flow regime is termed as fluidization. The turbulent fluidization regime, when do we get this turbulent fluidization regime? When there is extreme particle turbulence without large discrete bubbles or voids. When there are large discrete bubbles or voids, it is slug flow regime, and for turbulent fluidization regime there is extreme particle turbulence, but there are no discrete bubbles or voids. And this slugging flow regime, that is characterized by a particle dense phase transport which is facilitated by bubbles whose size is comparable to the pipe diameter. And the bubbling flow regime, it is characterized by smaller bubbles. So, slug flow they are characterized by larger bubbles, bubbly flow regimes they are characterized by smaller bubbles. In both the cases the transport it is facilitated by the air slugs or air plugs which are there. Now, in pneumatic conveying we have two other flow regimes which we do not have for fluidized bed. The first one is known as the plug flow regime. In the plug flow regime, what we have is they are characterized by particles which are transported as plugs and they are separated by air gaps. Okay. So, therefore, this particular situation we do not have for fluidization, we have it for pneumatic conveying. Here what do we find, that there is a plug flow regime, there are particles which are accumulated as plugs and they are separated by these particular air gaps. And sometimes what we find, these particles they fall from one particular plug to the next and then it forms something like the particle rain. This occurs when the cohesion force between the particles is smaller than the particle weight. Under this condition we get this. And the worst scenario for designers of pneumatic conveying is blockage. Now, this particular flow condition which causes blockage, that can also be considered as a kind of flow regime. So, these are the different flow regimes which we have for gas solid flow patterns. You will find that they are more or less similar to whatever we have studied for gas liquid flow patterns, like we have bubbly flow here, we have slug flow here, and of course, we have a fluidized flow here, which we usually there we used to call it as the dispersed flow pattern. It is sort of that. Okay? And in this particular case, we find that since particles, the moment we have particles, they are rigid, a solid loading becomes important. Due to that, we have this dense phase and dilute phase differentiation, we have something like the particle rain, we have suspension flow, we have fluidization and things like that. Okay? So, these were the different types of flow patterns which we studied for gas liquid, liquid liquid, gas solid and such other cases. Now, among the wide range of flow patterns that we have studied till now, it is quite evident that whatever we have studied, so if we notice little critically, we find that we can differentiate them into three types. One is the separated flow pattern. What are the distributions which lie within the separated flow pattern? It can be the stratified flow, the annular flow, film flow, jet flow, etc., etc. Okay? So, therefore, within separated flow patterns, we have stratified, annular and things like that. The other extreme is completely mixed flows. One is completely separated, the other is completely mixed. Under this condition, what we have? We have the bubbly flow patterns, the droplet flow when it is liquid liquid, or it can be mist flow for heated cases, okay, liquid droplets in gas. Then we have oil in water, water in oil, all sorts of such dispersed or completely mixed flow patterns, they fall within the dispersed flow pattern. And just like in single phase flow, we have laminar, we have turbulent and we have a transition. Here also we have separated, we have dispersed and a transition between the two. And interestingly, you will find that for most of the circumstances, we operate in the transitional regime, which comprises of the slug flow pattern, of the 3-layer flow pattern, and also when you study about the annular flow pattern, you will find ideal annular you hardly get. It is either the droplet annular, bubbly annular, things like that, where bubbles are dispersed in the oil in the liquid core, or maybe droplets are dispersed in the gas core and so on. So, therefore, ideally speaking, unless you have very high phase velocities or very low phase velocities, you hardly get completely separated or completely dispersed flows. Usually we encounter mixed flows, and that complicates the situation for two phase flow circumstances. So, therefore, here I just have the schematics, just in summary, the different schematics which show the dispersed flow patterns, the transitional flow patterns, as well as the mixed and transitional flow patterns, so that we can just in a nutshell you can have an idea regarding these things. Now, once you have learnt what can be the different flow distributions, the next important thing is you know the distributions, but you also have to know under what conditions different distributions exist. Unless you can pinpoint that under this condition this distribution will be there, under that condition that distribution will be there, unless you know this thing, it is no use learning the range of distributions which are available. So, therefore, in the next class we will be dealing with how to represent the range of existence of the different patterns under different flow situations. And after that, what I have decided is, see, we have talked a lot about flow patterns, flow regimes, etc., and how your conduit orientation, your fluid type, your pipe diameter, all these things, how they influence the distribution. Now, in the next class, what I have decided is, what I will do is, we will take the simplest possible case of two-phase flow. What is it? A single gas bubble rising in a liquid. Simply a single gas or some particular air volume rising in a liquid. And we will see that even for this particular circumstance also, how the conduit characteristics, how the fluid properties, they affect the rise of the single elongated bubble. So that it will give you an idea that when both the phases are moving, then how complicated the situation can be. So, I conclude here, the more or less the flow patterns we have discussed. We will be discussing the range of existence of the different flow patterns, and then we will be discussing simply the simplest case of two-phase flow and how it is affected by different circumstances, and we will be continuing our discussion in this particular way. Thank you very much.